హాయ్ గైస్, వెల్కమ్ టు ఏపీఎస్సి ఫ్రీ ఆన్లైన్ క్లాసెస్. ఈరోజు క్లాస్లో మనం స్ట్రెంత్ ఆఫ్ మెటీరియల్స్కి సంబంధించి థిన్ సిలిండర్స్ అనే టాపిక్ని చూద్దాం. ఈరోజు క్లాస్లో మనం చెప్పుకునే సిలబస్ ఏంటంటే థిన్ సిలిండర్స్ అండర్ ఇంటర్నల్ ప్రెషర్, స్ట్రెసెస్ అండ్ వాల్యూమ్ చేంజెస్. ఓకే, ఫస్ట్ we understand what is meant by thin cylinder. If the thickness of the wall of the cylindrical vessel is less than 1/15 to 1/20 of its internal diameter, the cylindrical vessel is known as a thin cylinder. In other words, the ratio of a cylindrical vessel, that is thickness to the internal diameter of cylindrical vessel, is less than 1/15 to 1/20. Okay. In case of thin cylinders, the stress distribution is assumed uniform over the thickness of the wall. Okay, we can assume the stress distribution is uniform in the case of thin cylinders. Next, we see thin cylindrical vessel subjected to internal pressure. This figure shows thin cylindrical vessel in which a fluid under pressure is stored. In this, a fluid is stored with under pressure. Fluid is under pressure P. D is the internal diameter of the thin cylinder. T is the thickness of the wall of the cylinder. P is the internal pressure of the fluid. L is the length of the cylinder. Okay, this is a length. This is the cross section of a cylinder. Then, on account of internal pressure, the cylindrical vessel may fail, splitting up into one of two ways. This is one way and this is another way. The forces due to pressure of the fluid acting vertically upwards and downwards on the thin cylinder tend to burst the cylinder like this. This is a first failure case. Due to vertically upward and downward forces. Okay, the forces due to pressure of the fluid acting at the ends of the thin cylinder tend to burst this. ఇలా ఎండ్స్లో యాక్ట్ అయితే ఫోర్సెస్ అనేటివి, దెన్ ద సిలిండర్ ఈజ్ ఫెయిల్ లైక్ దిస్. దిస్ ఈజ్ ఫస్ట్ ఫెయిల్యూర్, దిస్ ఈజ్ ద సెకండ్ ఫెయిల్యూర్. ఎనీ ఆఫ్ దీస్ టూ కేసెస్ మే occur. Next, we see stresses in a thin cylindrical vessel subjected to internal pressure. We have two topics, stresses and volume changes. We can cover it is very easily. Okay, when a thin cylindrical vessel is subjected to internal fluid pressure P, the stresses in the wall of the cylinder on the cross section along the axis and on the cross section perpendicular to the axis are set up. Okay, these stresses are tensile, are known as circumferential stress and longitudinal stress. Okay, circumferential stress is also called as hoop stress. What is the definition of a hoop stress and longitudinal stress? We can see now. The stress acting along the circumference of the cylinders is called as circumferential stress, whereas the stresses acting along the length of the cylinder in the longitudinal direction is known as longitudinal stress. The circumferential stress is also called as hoop stress. Okay, next we see expression for circumferential stress or hoop stress. This is the failure may occur in this. Okay, the P is the internal pressure. This is the internal pressure. D is the diameter, internal diameter of the cylinder. T is the thickness of the wall of the cylinder. Sigma 1 is the hoop stress in the material or circumferential stress in the material, sigma 1. For that, we can derive an expression based on this force due to fluid pressure. That means this small. Based on P, we can get a fluid pressure force, and based on the circumferential stress, we get a force. If you equating force due to fluid pressure and the force due to circumferential stress, we get circumferential or hoop stress. Okay. First we see force due to fluid pressure. Fluid pressure small p. Fluid pressure P into area, right? Area on which P is acting. D into L. How? This is the diameter. The P is acting in the diameter and throughout its length. Then the area will be diameter into length of the cylindrical vessel. We get the force due to fluid pressure. If you calculate the force due to circumferential stress, sigma 1 is a circumferential stress into area on which sigma is acting. Sigma is acting like this. This is the length, this is the thickness. Okay, this is the thickness T. This is the length and two sides. That's why 2 times of LT. Okay, 2 times of sigma 1 into 2 times of LT, we get 2 sigma 1 LT is the force due to circumferential stress. If you equating both force due to fluid pressure and force due to circumferential pressure, we get L get cancelled out. Sigma 1 is equals to PD by 2T is the circumferential or hoop stress. Okay, next we see for longitudinal stress. P is the internal pressure. We know D is the internal diameter of the cylinder. T is the thickness of the cylinder. Sigma 2 is the longitudinal stress in the material. Okay, sigma 1 is the hoop stress. Sigma 2 is the longitudinal stress in the material. If you observe, this is a figure for the longitudinal stress developed. Then force due to fluid pressure P into area on which P is acting. P is acting on the circular section, that's why pi by 4 into d square. This is a P. This is a P. It seems to be circle, that's why pi by 4 into d square we can use. Resisting force sigma 2 into area on which sigma 2 is acting. This is a sigma 2 is acting the walls. Okay, so I consider a circumference of the circle with multiplied with the thickness. I get a area. I multiplied the area with the sigma 2 longitudinal stress and I equate the force due to fluid pressure P into pi by 4 into d square is equals to resisting force, that is sigma 2 into pi d into T. Here one d is cancelled out. Pi get cancelled out. Then sigma 2 is equals to PD by 4T. In the first case, sigma 1 is equals to PD by 2T. By comparing these two, longitudinal stress is equals to half of the circumferential stress. Okay. This also means that circumferential stress is 2 times the longitudinal stress. So sigma 2 is equals to half times of sigma 1, or in another words, circumferential stress is 2 times of longitudinal stress. Both are same only. Hence, in the material of the cylinder, the permissible stress should be less than the circumferential stress, or in another words, the circumferential stress should not be greater than the permissible stress. That means the circumferential stress is sigma 1 should not be greater than permissible stress. Next we see due to volume change. This is the dimensions changes, how the formulas may change. We can see the circumferential strain. The circumferential strain formula will be E1 is equals to sigma 1 by E minus mu times of sigma 2 by E. This concept we come across in stress strain concept. If you substitute sigma 1 value and sigma 2 value in it, okay, we get PD by 2TE minus mu PD by 4TE. If I put common as PD by 2TE, 1 minus mu by 2. So E1 is equals to PD by 2TE, 1 minus mu by 2 is the circumferential strain. I hope this formula is understand. The next one is longitudinal strain. The longitudinal strain is equals to sigma 2 by E minus mu sigma 1 by E. If you substitute sigma 1 sigma 2 values, we get PD by 2TE half minus mu is the formula for longitudinal strain. But the circumferential strain is given by change in circumference due to pressure divided by original circumference. That is, E1 is equals to change in diameter by original diameter. This is the circumference. That gives us a circumferential strain. Similarly, for the longitudinal strain, delta L by L, change in length due to pressure divided by original length. If we equate these two, PD by 2TE half divided by mu, also formula PD by 2TE 1 minus mu by 2. This is formula. Okay. Next, volumetric strain. Volumetric strain will be delta V by V. These we can come across this in strain concept. Please refer. If you have any doubts, please go through once for the strain concept, and we can recollect. We can recall these concept again. 2 delta D by D plus delta L by L. Okay, substitute delta D by D plus delta L by L. That is E1, 2E1 plus E2. Substitute those values, we get PD by 2TE 5 by 2 minus 2 mu is the formula for volumetric strain. I hope this class will helpful for your preparations. In the next class, we see another topic. That is the last topic I can cover for the Appsc examination. Thank you.